What's going on, Yelani? So we finished with manometers. We're going to hydrostatic surfaces or submerged surfaces. I'm not sure what the hell they're called. But point is, this one, I believe in my opinion, was the hardest topic of fluid mechanics. If you could get this, then you'll be all right. So the problem reads, a gate having the cross-section closes an opening 5 feet wide and 4 feet high in a water reservoir. The gate weighs 500 pounds and its center of gravity is 1 foot to the left of AC and 2 feet above BC. Determine the horizontal reaction that is developed on the gate at C. So let's go ahead and get started. All right, so first step, like always, knowns, right? What do we know? We know we're dealing with water. That's a good start right there. So we know the gamma of water is equal to, we are dealing with feet. It is 62.4 pound per feet cubed. And the weight of the gate is equal to 500 pounds. They also give us right at the center of gravity, but we don't need that yet. I'm not going to write it down. Just it's good to know exactly where the center of gravity is, because at the end of the day, we're going to have to take a moment about the hinge, but you'll see why. So second step, a free body diagram. Let's give ourselves some space. Free body diagram. So this is our gate, pretty much. And this gate, to reach the surface, we're going to kind of draw a diagonal line up into the surface. Ooh, it's not the best, but it's cool. Right? This is our surface right here. We know there is a force acting here due to water and here due to water. So we don't know where they are. We don't know what the value is, but we're about to find out. Let's see. F2. It's asking for the horizontal reaction developed at the gate at point C right here. So there's a horizontal reaction. Doesn't matter what way you point the arrow yet. At the end of the day, it will fix itself once you find the values. You'll just get a negative, all that good stuff. And the weight of the gate, let's just put it here. And then there's a reaction at the hinge. So at the hinge, let's label this point H. There's a HY. Then there's a HX component. Again, the signs don't matter. They'll fix themselves at the end. So first step in these problems, there's a crazy approach on these, but first step actually is to let's find the force 1 first. F1. That is going to equal pressure times area, right? That's force. Now in this case, it's from manometers, we know that pressure is equal to gamma times height. And then, right? So we're dealing with water, we have gamma. Height, in these problems, height isn't always straightforward. Sometimes you got to look for it. In this case, let's see, what can we do? Okay, well, first thing we got to know that it goes in, it's 5 feet wide, meaning it goes into the paper 5 feet. Okay, and we could go ahead and start plugging in some stuff. Let's see. Well, you know what? Before we start plugging in, this is a 3, 4, 5 triangle. You see that? This is a 3. 3 squared plus 4 squared. The height is equal to 5. Right here. So we know this is a 3, 4, 5 triangle. This is a 4, 3, 5. That means we're able to get this distance, horizontal distance, because we have the height right here. So this is 8 feet. Let's see. We know cosine of theta is equal to 4 over 5, right? In this case, 4 over 5. So that means cosine theta is equal to 8 over some value. the distance we want from here to here, right? So let's go ahead and find that number. We're gonna, let's just put x here for now. We set both the thetas equal to each other. So then we get 4 over 5 is equal to 8 over x. If you do the math, you get x is equal to 10. So here's what, 10 right here. All right. So now we know the area. So what we do here with this force, this is trying to tell us how much force is acting on this block square. Because you remember it goes into the paper, so it's a square. So that area is 5 feet, right? The height right here, this length, times the width. So we know, let's put it over here. Gamma, it's water, 62.4. Height, in this specific case, when you're finding the height inside the force equation, it's pretty much your vertical height. Doesn't matter where it is, right? It's just your vertical height, and it's halfway between this point and this point. So in this case, it's 8 plus 2, right? Because 4 over 2, halfway vertically. So that is 10 feet. I'm not going to put units. Just follow along. 10 feet. In this case, area is 5 times 5. So now we got our force 1 is equal to 15,600 pounds. So cool, we found one force. That's good news. Now, next step is pretty much to find where this force is acting. So you don't know if it's acting here or here or here, what distance pretty much. So that's why we use, I forgot the name of the equation, but this is the equation you use. So find where F1 is acting. There we go. There's the equation right here. So Y1, in this case Y1, right, is equal to IXC YCI A1 plus YCI. I forgot the names of these formulas, I'm gonna be honest with you, but it doesn't matter the names, you just gotta know how to pretty much calculate it for whatever reason. So I, in this case, it's a square. So if you remember from statics or dynamics, I'm not sure, you got to take statics for this class. So statics, for a square, IXC is equal to 1 over 12 BH cubed. Oh, okay, so that's IXC. Area, we found it here, right? Area of 1, that's just 5 times what it goes in. And then YCI. So YCI is the distance halfway to the, but along the surface. So in this case, we want the halfway point here, but you got to go all the way up to the free surface. So it's 10 plus, this is 5 feet in length, right? 5 feet. So it halfway is 2.5. So YCI is equal to the 10, right? 10 plus 2.5, halfway between here. Now again, the difference between this height here and this height here, this one, when you're finding a force, that height you only care about is the vertical height. In this case, you want the height along the surface all the way up to the free surface, along the surface of the square, and then all the way to the free surface. So that's why YC1 is 10 plus 2.5. That's going to be 12.5. Let's go ahead and calculate this one right here. IXC, so in this case, it's going to be 1 over 12, right? Base is 5. Base is the width, how much it's going in. So that's 5 right there. And then the height is just the height reference from to the, again, vertically. Now, in this case, they're both 5, so it's easy to obviously plug and chug here, but you got to know which 5 this is. This 5 corresponds to the height. It's your base and height. So your base is the one that's going into the paper. Just keep that in mind. You'll see in the next problem why that could mess you up if you don't do it right. IXC, okay, you know what? I didn't calculate this number, so, but it doesn't matter, right? At the end of the day, Y1, you got your IXC from this. You got 12.5 for YC1, and you got A1 as 5 times 5. That's your area. If you do the math, you'll get 12.67. So that's your Y1 right here. Okay, so that's pretty much the goal in these questions. It's find the force and where it's acting for every single one. In this case, we have 2 forces, well, 3 with weight. But that's all you need, because at the end of the day, you're going to take a moment. And this is measured in feet, FYI. If you do your units, you should get feet. But just, this is feet, this is force. Force times feet. That is a moment, which is what we want at the end of the day. So let's do step 5. Now let's do F2. F2 is this one right here. There's a force acting right here. And again, that's pressure times area. Area of 2. Now, this is what's going on here. So this is 3 feet, right? You see that? So you learn from machine design, and I think statics too, I can't remember. But this is what's going on right now. This is the gate. Just this, I'm sorry. Just this. That's the gate, and it's going in some depth, right? Now here, we got a force. It's a distributed load. That's what it's called. I figured by now you'd be taking some advanced classes, so you could always just YouTube it if you don't know what a distributed load is. But pretty much it's saying there's forces here acting evenly. And since it's horizontal, it's acting in a perfect square. So, you know how... So right here, that's kind of what the specific weight means. 62.4 pounds for every feet cubed. So in other words, if you have a volume of water, 1 feet length, width times height, each one, that's going to be 62.4 pounds. Now, in this case, we got 3 feet, and then it's also going in, right? We got a, like that. It's going in 5 feet. So like that. It was not the best drawing, but 5 feet. This is 3 feet. So that's pretty much all it's saying. This force is acting uniform on this surface right here. So, and then what I wanted to say from that YouTube reference, you're gonna know that for any scenario like this, the force always acts perfectly in the center. So there's you could summarize all this distributed load with one single force acting at the very center. So like that, you know, one very big force that accounts for all of them. Okay, so we go ahead and keep going, right? This is gamma H, A2. Same thing as up here. Let me move it up if you can't see. But that's gamma H2, and that is equal to 62.4, right? Your gamma times your height. This one's acting 12 feet, right? 8 plus 4, it's your vertical height. 12 feet times 3 times 5, right? What it goes in. So 3 times 5. This force value is equal to 11,232 pounds. So we got our force 2. That one was easier. It was horizontal. Nothing too bad. We know force 2 again, since I told you, right? It's acting at the very center. You could replace this whole distributed load with one single force, this one, and that is acting 1.5 feet away from the edge right here, right? That's 1.5 feet. So that we should be good to take a moment. Again, we didn't find Y2 for this one because Y1, in this case, right, let's start all over. F1, there's a force acting here. We don't know what the hell that force is, right? When we use Y1 to find that force, that tells us exactly where it's located. So in this case, 12.67, it's acting 12.67 feet away from the surface. So it's 10 plus 2.67, so just a little over half, which is around right here. Well, it's all right. This is halfway. There's probably like 2.67, yeah. So it's 10 plus 2.67. That's where 12.67 is coming from. In this case, we'd have to find Y2 because we already know off the bat this distance is 1.5. So we're good. Now, you're probably wondering, well, it's asking for the horizontal force here, right, at point C. And in this case, we're going to take a moment about point H. Now, you're asking why point H? We could take it anywhere. Makes no sense why you would do that, though, right? Let's say if you want to take it here for whatever reason. You got to find F1 times this distance, and then you got to include HY and HX, because this HX is acting at a distance here, HY is acting at a distance here, FC is acting at a distance. There's too many unknowns. So if we take it about point H, we don't have to worry about HY or HX, just F1, W, F2, and then we're looking for FC. All right, so let's go ahead. Take a moment. So this way's positive like always. Some of the moments about point H is equal to 0. It's equilibrium, right? Which that is equal to, all right, let's do it. F1. Let's do F1 first. No, I'll just write the equation instead. F1 times your distance, right? That distance is, well, we know all this is 12.67, but we don't want that 10 just up to this point, so that's 2.67. 2.67. F1 is going to make it turn clockwise, counterclockwise, and that's a positive. Oh, that's a positive right here. So cool, there's a positive value. F2 is going to make it turn clockwise, so that's a negative. F2, and the distance between F2 to H, it's 1.5. From here to here, that's 1.5. 1.5. Now, our weight plus, well, weight is going to make it counterclockwise. So that's a positive. Weight times, it says here in the question, the gate weighs 500 pounds. Center of gravity is 1 feet to the left of AC. So this is AC right here, 1 feet to the left. So that means weight is acting 1 feet away from the hinge. 1, right? Now finally, FC. FC is 4 feet away from the hinge, right? There's the force here. So, and that's going to make it spin clockwise. So it's a negative FC times 4. That equals 0. All right, we're almost there. Start plugging in some numbers. We got 15,600 times 2.67. Cool. Minus 11,232 times 1.5 plus the weight. Weight was 500 times 1 minus FC times 4. That equals 0. It's an equilibrium. Cool. If you do some mathematics, 41652 minus 16848 plus 500 is equal to FC4. I just moved it that way. You'll get FC is equal to 6,326 pounds. And there's your answer. We found the reaction at point C, the horizontal reaction. Now, key takeaways from these problems is the first one I'm doing. it usually starts off this way. You start with the free body diagram. You got to see exactly what's going on. Now, this is potentially a midterm problem because they're going to quiz you on a horizontal distance. So you have to know what h is, how to get this h, and just don't confuse it with the heights in this equation. So this height, again, it's just the perfect vertical height halfway on whatever it is you're analyzing. So it's, in this case, it's 8 feet times plus 2 more feet, halfway, for F1 right here. For F2, in this case, it was a perfect uniform distributed load, so that one was easier. YC1 is the distance halfway perfectly like along your surface, right? Along this surface, and then continue it all the way up until you get to the free surface. That's YCI right here. Y1 is when you take into account the moments of inertia. I think that's what they were called. In this case, we're dealing with a square gate. So it's 1/12 base times height cubed. Again, this 5 as the base is the width going in. This 5 is the height. You know your area, right? Area of the surface. Pretend you're looking at it this way. It's a perfect 5 by 5. What else? I believe that's it. So, I mean, the problems get a little bit more crazy. You'll see some other examples I'm gonna do, but that sums it up on this one.